Hello, good afternoon. My name is Anayat Fanda, PhD in aerospace engineering. The topic of my presentation is finite element-based analysis of damage induced from low velocity impact on unidirectional fiber reinforced cross-ply laminate structure. I am originally from Ethiopia, from Defense University College of Engineering, and I am doing my PhD in Indian Institute of Technology, Campo. Actually, I have already done my PhD as of last April 25, so it is already done. So the presentation outline includes the following points. Introduction is there, aim and objective, research methodology, result and discussion, conclusion on finding, contribution of the work, and acknowledgement also be included on that. So, as we know, composites are material system which compose of materials of two or more constituents, and the combination of these two or more dissimilar constituents yields composite material. What are those two constituent material basically which we are using? This includes the fiber and the matrix materials. Okay, so the fiber material, which is a transversely isotropic material, and the matrix material, which is homogeneous material. And we also introduce some interface materials in the case of preparing composite. So the combination of this material will give us either a representative volume element or the representative unit cell of material. And then the unit cell or the representative volume element gives us the unidirectional line. So as we see here, the fibers are oriented in one direction only, so that we call it as UD composite. So it is based on the fiber orientation. When the fiber oriented in multiple direction, it cannot be UD. So this is UD composite, and the lamina created from UD fiber, and the matrix is called unidirectional lamina. And the combination of unidirectional lamina, that means when we are systematically stacking unidirectional lamina and the interface element together, then we can find a laminate. And the laminates are raw materials for the preparation of structure. So most structure, which especially in the case of aircraft body, made from such combination of material. So this is the method how we can create unidirectional fiber reinforced composite. The use of laminated composite for structural application results in high reduction in weight, and it is characterized by high strength and stiffness. At the same time, high reduction in strength also, weight is also result. And due to this reduction in weight, that also leads to reduction in fuel consumption in the case of aircraft. As you know, the cost of fuel increasing day to day. So the use of lightweight material enables high reduction in the cost of on the consumption of fuel. And then at the same time, it results in the cost of flight, and also due to that greenhouse emission reduction also be achieved. For example, in particular Boeing, 20 to 25% of carbon dioxide emission and water vapor and nitrogen dioxide, these things are reduced to much number. So however, the use of this laminated composite is very limited for the out-of-plane loading conditions, such as impact loading. So this impact loading causes a critical damage in the structure that the damage is highly insidious and which is not easily detectable at the impacted phase. Therefore, the structure will severely damage without showing any visible damage. Therefore, the damage is known as barely visible impact damage. So this work emphasizes on the finite element-based numerical modeling of laminated UD fiber reinforced polymer composite for the damage induced from low velocity impact and response of structure to the load. Maybe the response are elastic or it can be damage response. Actually, structures impact from various shapes of objects, especially in the maintenance sector or at the time when aircraft move from place to place on the inspection phase. That time it encounter with various impact from various shaped objects. Okay, some of the objects are stationary. Sometimes the fuel supplier tracks also can cause some kind of scratch on the structure. So these are some shapes which is expectedly results in impact. And the damage wounds which we can observe on composite structure from general type of loading are shown here. So these are fiber failure in tension, fiber failure in compression. In tension, we can observe the fiber fallouts. Okay, here we can see fiber fallout. In compression, we can see the fiber kinking or the kink band formation of the fiber. In transverse tension, we can see the separation of the matrix material. And in the transverse compression, we can see an inclined fracture plane. Okay, so it fractured in this manner. So this fracture plane is considered from 50 to some 56 degrees and and also we can observe a longitudinal matrix crack, and also transverse matrix crack also be observed, or the combination of the matrix crack. And this is the fiber matrix debonding at the matrix fiber interface debonding. Okay, so these are some of the damage. Here we can see in laminated structure, we can see matrix crack, we can see fiber fracture, and we can see the delamination. Okay, so delamination at interface also. So these are some of the damage patterns. So how we can describe this all together? Matrix crack, interface delamination, debonding at fiber matrix interface, fiber breakage, and finally ultimate or catastrophic failure of structure. So this is the sequence of the damage in laminated structure. So the aim of this research work emphasizes on implementing computationally reliable three-dimensional FEM technique for numerical analysis of damage induced from low velocity. One, UD fiber reinforced composites, particularly for aeronautical application, with the help of Abacus explicit FEM tool. So the research methodology followed are reviewing various research works, identifying useful numerical methods, damage models, and failure criteria, developing the UMAT code, which can capture 3D constitutive material model, failure criteria, damage evolution techniques, and implementing the UMAT code to the explicit FEM tool, and creating geometry of ASTM D7136 standard for cross-ply laminate. So this is the methods. And the damage model modeling strategies, we have a hierarchical or homogenization modeling strategy and concurrent, or this is splitting from higher order to lower order. It's called concurrent modeling approach. So more of both of the techniques are applicable. It needs the knowledge how to implement the techniques. So how the FEM techniques used in current work? So our finite element formulation of governing differential equation starts from the dynamic equation. That is the dynamic equation of structure. I can explain that dynamic equation with some pen. Yeah. So we have, most of the time we have mass. Whenever there is a dynamic condition comes, mass is there. And we have acceleration plus we have damper and velocity is there. And the stiffness K x, this displacement x, which is equals to F external. So our explanation starts from this point. So using the forward Euler method, we will find for the mass inversion. Okay, so this is explicit finite element method, so that we'll do the forward Euler iteration method to determine the parameters like acceleration, displacement, and the velocity. So that this equation shows the forward Euler technique of finding parameters. Okay. So on that, the constitutive relation also defined in terms of stress-strain relation. We have stress Ij for Ij1 to 6 and Cij. Actually, Cijkl. It is not only Cij, but Cijkl. It is a tensor with fourth order, and this is with KL. Okay, this is KL, not IJ. So with help of this equation, we'll define the constitutive material relation, that stress-strain relation, with the help of stiffness. And the Haschen-Pack failure criteria for damage initiation of UD lamina is defined. So for that, we need fiber failure and tension relation, fiber failure and compression, fiber matrix failure and tension, and matrix failure and compression relations will be defined. So this relation is defined in terms of the strength parameters and the stress parameter. So the material strength parameters and the material strength parameter. For example, if I define F of T, fiber failure and tension, okay, fiber failure in, okay, this is the failure index, fiber failure and tension is equals to, we have sigma xx over x. This is strength, x strength and tension. X strength and tension square plus sigma xy over, okay, here s 1, 2. Let me define this thing in terms of the direction, fiber direction parameter 1, 2. Okay, sigma 1, 1, sigma 1, 2. Okay, so this is a square plus again sigma 1, 3 over S13 square. S13 square. This is the one of the Haschen failure criteria. Greater than or equal to 1, then the damage will initiate. Okay, sorry. Okay, so this is the damage initiation for fiber. Similarly, we define for fiber compression, matrix tension, matrix compression case, the failure index will be defined. Again, then defining the damage variables for the fiber in the matrix in the local and in the global form. And then this DFT and DFC, DMT, DMC are the solution-dependent state variables. These are damage variables, which determines the damage evolution parameters. And the damage evolution criteria for the laminate is simply defined using the damage variables with the failure index parameters. Then the material model for damaged laminate. Initially, this one was undamaged material, which is pristine material, and this is for the damaged material, which is defined in terms of the damage parameters with undamaged stiffness of the material. So then the next is the interface damage initiation and evolution parameters. So interface damage initiation makes use of the quadratic interaction between the traction and the normal traction and force. So we use traction separation method for the damage initiation, which is a quadratic traction interaction. Okay. And the damage evolution follows the Benzegang and Cannon fracture criteria. There are three fracture parameters: critical fractures, critical energy release rate in the first mode, second mode of fracture, third mode of fracture are there, and the other fracture parameters G11, G11. G12, G2, G3. These are also fracture energies. So we can define them in terms of fracture energy. Okay, so this is the BK curve fitting parameter. So in order to initiate delamination at interface, GT must be greater than GC. So which one is GT? Sorry, I didn't define the GT. Yeah, this GT. This GT is equals to the sum of G1 plus G2 plus G3. Okay, so this is GT. And GC is this parameter, okay? Critical energy release rate, which is defined here in the traction separation curve. So here we can observe this is the linear traction, linear relation between traction and separation. And then once it reaches to this point, the material start to evolve. So this is the material degradation scheme of the interface material. Okay. Okay, once we decide this, let's take a rectangular STMD 731 standard cross-ply laminate, which is modeled with a deformable plate model and a rigid impactor model. And the dimension is 75 by 125 by 4.16 millimeter. This is standard dimension I took. And for all for each fixed boundary conditions considered, and 3 different velocities are allowed. Okay, so which produces different energy, impact energy. This one produces 1.25 joule energy. This one produces 2.5 joule energy. Sorry, and this one produces 5 joule energy. So at the same time, the material stacking sequence is 090 symmetric, which is cross-ply, okay, and T721 carbon epoxy material is considered, and this is the meshing scheme used. So we used the localized mesh as the impact critical region and coarse mesh at the far edge. Okay, So, and RS3D4 rigid element impactor is considered. Okay. And the 8-node 3D solid element or C3D8R element is taken for the laminate, and 10 micrometer interface which is modeled with cohesive 3D 8 element selection. So the total number of elements considered here is for laminate 107,200 elements in lamina, and 8,400 elements for interface. Okay, this is for interface material, and this is for the lamina material. So totally these elements are involved. The result of TENT can be expressed in terms of history output and the field output. So these are the history output from the current model. So the history outputs represent in terms of deflection versus time curve for 1.25 for 2.5 joule, okay, for 5 joule, okay. So these are deflection history. At the 1.25 energy, 1.16 deflection obtained, and it takes 4.1 millisecond to, and the second for 2.5, 1.66 millimeter deflection is obtained with 4.19 millisecond, and for 5 joule, 2.48 millimeter, which is achieved with 4.77 millisecond. Similarly, the force time fluid shows various forces: 2,200 newtons, 310 newtons, 3,650 newtons are the loads obtained. So the basic thing from the force time curve we can observe is we have an undulation here which shows the damage initiation point. So in the 5 joule, the damage is initiated at this time interval, that is in 1 millisecond. So that is damage initiation load, and the damage threshold load is obtained at this point, which is 3650 newtons. So that is at which time it achieved. That is this time. That is less than 2 microsecond, no, 2 millisecond. It is about 1.8 millisecond achieved damage threshold load. Then after the structure comes back to zero position, that implies the elastic response of the material. Okay, and then another is the energy time curves. This energy time curve shows the amount of energy dissipated. In this case, this is the amount of energy dissipated. This, again, in this case, we can observe, so our zero is here. So this is the amount of energy dissipated for 2.5 joule. And similarly for 5 joule, we can observe this amount of dissipated energy. So, and then force deflection curve. So the force deflection curve also, the area under force deflection curve shows the amount of energy dissipated. This area shows ED, energy dissipated. Okay. Yeah, so this is what we can understand from these curves. Finally, the amount of dissipated energy for 1.25 joule is 4%, for 2.5, 9.6%, and 5.5%. So we can see high energy dissipation at the higher impact energy. And yeah, so when I summarize this work, the current numerical simulation underestimates the energy absorbed and overestimates the maximum peak contact force. When comparison is made with the existing literature, we can observe. So the variation in the result is due to many reasons. One is the presence of material or property variability. Another assumption of rigid constraint conditions, and the assumption of contact definitions in FEM. So we used general contact algorithm, but it needs particularly different contact conditions, especially in the thin lamina, thin interface, and at the lamina point, it needs some different contact mechanism. And the finite element discretization also one of, and the partition of geometry for mesh refinement purpose is another case. So when we come to second case, means impact field output, we have such damage we can observe for 1.25 joule. For 2.5 joule, we can see more damage here. And for 5 joule, you can see very extended damage. And the interface damage also for 1.25, for 2.5 and 3 joule, we can see. So this is the interface damage or delamination damage. And then in general, how we can define the fiber, the matrix damage. Let's see. For fiber, the top and the bottom part, how we can observe. So the fiber tension at the top, no damage. Fiber tension at bottom, no damage. Fiber compression at top, there is damage. Fiber compression at bottom compression, fiber has no problem. And then when we come to matrix tension at the top, there is. Matrix tension at the bottom, there is high damage. Matrix compression at the top, there is. And matrix compression at the bottom, there is damage. So these are the damage patterns observed in fiber and the matrix separately. This is using continuum shell element modeling technique. I use this for comparison purpose. So this is a delamination shapes. Okay, at the top interface, again second top interface, third top interface, fourth interface, cubes, and the last 6 interface. So we have 8 laminate and 6 interfaces because we are not using interface at the 90-90 position. And this is the X-ray radiographic image of delamination shapes. Most common delamination shapes are 90-0 laminates. Okay, so the orientation of delamination shapes define clearly similar shape, or that is bean-shaped delamination. So when I conclude my work, low velocity impact model for various low level of energy have been discussed, okay, have been studied, and comparison have been made with experimental work of researchers and found a very close agreement and in consistent manner. The numerical model predicts matrix damage like matrix crash, cracking, matrix crash through the thickness, delamination at interface, fiber failure in tension and the compression due to low velocity impact. And the cohesive 3D8, this solid 8-node solid element using ViewMath provides damage information through thickness. Hence, it predicts the damage modes more accurately when compared with the this continuum shell element using Abacus inbuilt model. The damage observed includes fiber tension, fiber compression, matrix tension, matrix compression, and delamination and matrix crash damage as well. I would like to express my special appreciation to my guide, Dr. PM Mohute, for his guidance throughout my research work. I would like to express my gratitude to my sponsoring organization, Ministry of Ethiopian National Defense, and my home institute, Defense University College of Engineering, where I did my advanced diploma in mechanical design and drafting, Bachelor of Technology in Mechanical Design, Masters of Technology in Aerospace Propulsion. I would like to thank IIT Kanpur for providing opportunity to pursue my PhD research work since July to April 22. So these are the reference which I used through my study. And so thank you very much. If any comments, suggestions, and questions, you are welcome.